I've lost a bank of lights, so I'm sorry if I'm in the gloom. It's probably for the best if you can't see me so clearly. But yeah, so yesterday we looked at connected particles moving on a horizontal plane. This is another sort of connected particles question, where we haven't got two things connected. We've got something inside something else, and that's normally either in a lift or, in this case, a scale pan, which is like one of those things you use in science to weigh things. But it's basically a lift. It's being raised like this, and this is like a lift with two people inside it. It's just a small, it's a tiddly little lift. So our second sort of connected particles then, I'm going to call this lift problems. So we are still dealing with connected particles. And because we are dealing with connected particles, these questions can be answered in the same way as the first sort, by looking at the problem at different levels. So we're going to start by looking at the problem from the point of view of the whole system. So we're just going to look at this thing as a single entity being lifted by a force. I've no idea what's inside. I'm just thinking about it as the whole system. Okay, so I'm firstly going to think about the whole system. So the whole system is, I've got something which has a total mass, a light scale pan. Remember, that's one of those assumption words. Light means it has zero mass. So it has a total mass of 1,000 grams, 1 kilogram. And it is being raised using a string, pulling up. And that's causing it to accelerate at 0.5 meters per second squared. There is another force in the situation, isn't there? Because now we're moving vertically, we do need to consider the weight of our lift, which in this case, because it has a mass of 1 kilogram, is 1 times 9.8, 1g. So go on, see if you can start off by using F equals ma. Let's agree that up is positive, so we're going to resolve vertically where up is positive. Let's use F equals ma. We know we're in Newton's. Shame Newton didn't come from Luton, but there we go. It's Newton's second law, F equals ma. See if you can work out the value of the string, the tension in the string, yanking it up. So I know the force going up is going to be bigger because it's accelerating up. So it's going to be, and remember, g is a constant, its acceleration due to gravity is 9.8. So take T pulling up, 1g pulling down, T minus 1g is the resultant force. and that's equal to mass times acceleration. So we bit of algebra, and we get 10.3. We've answered the first part by considering the whole system. We have no idea what's inside the lift. We're just dealing with it as one whole thing. Okay, part B then. We need to look inside the lift. Inside the lift we've got two masses. We need to find the force exerted by mass on mass B by mass A. So mass A is pushing down, isn't it? And it's a bit more complicated. Have you ever gone up in a lift and suddenly you felt heavier because of the acceleration? Well, that's the effect of that acceleration. So it's not as simple as saying the force exerted by A on B is 0.4 g. That would be true if it was stationary. But because we're accelerating upwards, it's not as straightforward as that. So one option, and I have to say ultimately this is a fruitless option, but one option, having considered the whole system, is just to consider the situation for B. Let's consider B, because we want to know what's the force pushing down on B from above, from A. So it would seem very sensible, therefore, to consider B. I'm just going to start a new pen. So B is sat there inside the lift, or the scale pan. The lift is pushing up on it, so that's some force pushing up on it. And A is pushing down on it, so we'll call that the force of A. And it's accelerating upwards, because we know it's accelerating, the whole system is accelerating at 0.5 meters per second squared. But I can't work with that, because I've got two unknowns. F equals ma would be r minus A equals 0.6, because it weighs 0.6 kilograms, times 0.5. So all that would tell me is the difference between the two forces. It wouldn't tell me what each of the forces were. So considering B is fruitless, because we've got two different forces that we don't know. So instead, we have to consider A. So this is a bit different to the two particle on a horizontal plane problem, where it didn't matter which particle you used. I've got to consider A. So let's think about the situation for A. A's sitting there, and all A feels is a force shoving it up the backside like that, okay? Because it's accelerating upwards. It's accelerating at 0.5 meters per second squared. We don't know whether that force is coming from B or whether that force is coming from the lift. It's just a single force shoving it upwards, and it weighs 0.4 kilograms. And so it's quite easy to work out that force there. That effectively is the force that B is pushing up on A. But hang on a minute, that's not the answer to the question, is it? Except Newton, he had something to say about this. He had a third law. And that third law said, when you've got two particles in contact with each other that are moving, the force exerted on one is the same as the force exerted in return. For every action, there's an equal and opposite reaction. That's Newton's third law. Otherwise, if the force B was exerting on A was more than the force A was exerting on B, A would crumple. It would crumple. So at that interface, we've got equal forces. So in order to answer part B, I'm actually working out the equal and opposite force to the one we want. This force here is not the one we want, it's the equal and opposite force to the one we're after. That's Newton's third law that says if you want to know the force pushing down, it's the same as the force pushing up. So this is nice and easy. Let's resolve upwards. That force pushing up, which we'll call F, is equal to 0.4 mass times acceleration. So that's 0.2 newtons. Now hang on a minute, what have I done? What have I forgotten? What have I forgotten? I've forgotten something?
Negative sign?
No, I haven't taken into account the weight of the block, have I? Sorry. So the other force in that picture is that it's got a weight of 0.4 G pulling down. So my force pushing up is F, the force pulling down is 0.4 times 9.8, and that equals mass times acceleration. Go on, quickly work out F for me. So we should get 4.12. So G is 9.8, so 0.4 times 9.8, add that on to 0.2, and gives you your answer. Okay. Now our horizontal two-particle problem stopped at that point. 2 questions. We'd looked at the system from 2 directions. Sorry, Sean, yes?
Doesn't the force exerted on mass d by A need to be negative if we're defining it?
Okay, so we would with a force we wouldn't have.
The force is a vector.
Okay, yes, but the direction is implied by the question. So the question says by mass B, sorry, on mass B by mass A. So that's already implied that that's a downward force. Yeah. I'm just going. I think I'll just double check that. Don't want to. They just say downwards. Yeah. Okay, so part C causes a bit of a problem. Surely I have looked at this from every angle now. I've looked at the whole system. I've looked at B and found I couldn't help work with B because there were 2 variables. So I've looked at just A. Well, there is a third way we can look at this problem. And that is to look at just the lift. Or I know this is a scale pan, but these are so often lift questions that I'm considering this to be a tiny tiddly little lift. Now you might say, well, haven't we already considered the lift up here? Well no, what we did up here was we didn't know whether it was a lift. We just knew there was a box with a mass of 1 kilogram moving upwards. Now we're just thinking about the lift. And the lift is being held upwards by a force that we calculated in part A, 10.3 newtons. And it, like everything else in this question, is accelerating up at 0.5 meters per second squared. But you know when you've had like a big meal, and you feel like really, the lift as it's travelled up thinking, God, I don't feel quite as light as normal. There's something inside me pushing down. And yeah, so it doesn't know what's inside, but there's a force pushing down on the floor of that lift. Now we know it's the 2 masses, but the lift doesn't know that. And that's the force we're trying to find. The force exerted on mass B by the scale pan is a force pushing up. Well, we can't calculate that. We calculate the equal and opposite force pushing down. Newton's third law says the force pushing up by the floor of the scale pan on those masses is the same as the force pushing down by the masses on the floor of the scale pan. So let's call it F again. So I'm going to use, sorry, I've been silly to try and put it all on one. Apologise for those on the video. There we go. So we're now just considering the lift. So it's a really simple situation. And oh, hang on a minute, have I forgotten the mass of the lift again with a weight? Well, no, in this case, it's a light scale pan. There is no mass, so there's no extra force this time. So it's really, really easy. I've got F equals ma, force going up 10.3 minus the force pushing down, F, is equal to the mass, which is 0, times 0.5. So that means the force pushing down is just 10.3, because that's 0, add F to both sides. So these lift problems, I think, are really complicated because of the whole Newton's third law thing. But the good news is they tend to be quite formulaic, so they tend to be whole system, one of the masses, just the lift. Okay? So we've got a little bit of time to start it now. The question which follows that route is 172, question 5. I think that's, there we go. Yeah, that's the one. So go on, have a go. So that is on page 171, question 4. Page 171. There's one key difference with this. It's not a light lift. The lift has a mass in this case. So when you get to that third stage, there is another force pushing down. Okay? Let me just stop the video. Okay, so we're talking here about connected particles and pulleys. The third sort, we've had horizontal motion, and we've had the lifts, and now we've got these pulleys. So coming back to you with that question just a minute, Arthur. So I've got P and Q. P weighs 2 times some constant, and Q weighs 3 times some constant. So what is going to happen when I let go?
Q's
going to fall, yeah. So we're going to get an unbalanced force. The only two forces here are well, sorry, no, that's not true, but the only thing affecting which one falls is the fact this is heavier. So we're going to get acceleration going in that direction, and we're going to get acceleration in that direction. And because the string is inextensible, we know those two accelerations will be the same. The forces involved, well, both of these have got weights. The M is a pain, but actually it's a pain that disappears fairly soon. That's pulling down, but there's also that string's holding them up. Even Q, which is falling, that string is it's keeping it from falling faster. So I know M is a constant, it's not a variable, so I'm not worried about M, but I am worried about the fact I've got two unknowns in this situation. I don't know the tension and I don't know the acceleration. But there's good news. Because all we're going to do is we're going to lop my diagram off there, and that's going to give me two separate systems. So I've got just P, so P I can write an F equals MA statement for that one, and I'm going to do that by considering up as positive. Now, that's not going to allow me to work out the missing values, but I can certainly write an equation. I can also consider just Q. I can write F equals MA for that one. I'm going to consider down to be positive. Don't have to, but it just means I'm not dealing with any negatives. Sorry, the accelerations are the same, but the fact the string is light and extensible means that the tensions are the same as well. So what I'm going to get here is an equation with T and A, T and A in it. I'm going to get another equation here with T and A in it, simultaneous equations. If I can solve those simultaneous equations, I can find my two missing values. Where I have two missing values, I need two simultaneous equations to solve it. So see if you can get somewhere with working out the value of T and A. And for those who are quick with that, let me add an extra question. I want to know, assuming that the P doesn't reach the pulley, I'd like to know how far both of the weights travel in the first 4 seconds. Okay, so that's your additional question for those that move a bit quicker. So I don't have to do it this way, but I've rewritten both equations as T equals. So this one, I had tension going up minus the weight pulling down equals mass times acceleration. And for this one, I chose down to be positive because that's the way it's accelerating. So I had weight take away tension equals mass times acceleration. And it's quite easy to rearrange those as T equals. T is the same on both sides, so I can just make Harrison, what does that allow me to do that makes this very easy all of a sudden? I've rewritten both of my two separate equations as T equals. What can I now do to make it a whole lot easier? I know, but what's my first step of simplifying going to be with that equation?
Just make both sides the same, so you can get the 3MA on that side and 2MA.
I'm going to do something else before that. Can anyone suggest what I can do straight away here? Divide by m. Yeah, now I can only do that if m isn't 0, but I mean it can't be 0 because you can't have 0 mass. So yeah, I'm going to divide everything by m. And don't forget, g is a number I know. I know what g is. It's 9.8, so that's 19.6. And 29.4. And then, as Harrison was suggesting, you can then just simplify. I'm going to add 3 a's to both sides and take that away from that, so that just gives me back to 9.8, because that's 2 lots of g and that's 3 lots of g. Should be able to do that. Now, sadly and rather frustratingly, the tension is still going to have an m in it. I can't get rid of the m's. So I've got 2 ways of working out the tension. I can either use this or I can use this. So I'm going to substitute it into the P equation. So I've got 2 lots of m times that, and 2 lots of m times 9.8. So whatever 9.8 plus 1.92 is. So that's the value of the tension. Yes, sorry, have I made a mistake?
I got 1.96 for the acceleration. 1.96.
1.9, have I? Did you get his or mine?
Yes.
Where have I gone wrong? Right, it's probably just a calculation error, isn't it? Where have I gone wrong? 5A. Just double check. No, it's G divided by 5. Have I done 9.8 divided? Oh, I'm sorry, I've done 9.6 divided by 5. Thank you. Well done. Remind me when we're next in my room. Sorry, 1.96. So that's going to be wrong, isn't it? So I've got. Oh, that's wrong. So that's not 1.76 meters. M is a constant, so it's 11.76 times m newtons. And if you did the 4 seconds thing, you should have found it went 15.68 or 15.7 meters. That's just using SUVAT because we now know the acceleration and we know its initial velocity was 0. There's another there's another way we can look at this system, and that's to consider the poor old pulley. So the poor old pulley has so far been ignored, but it is experiencing a force of its own, or rather forces of its own. So what force does the pulley experience? Well, the pulley experiences a tension from both sides, because if you've got the tension pulling up there, in order for the rope not to snap, you've got a tension pulling down there in response to it. So the pulley, the force on the pulley is 2 lots of T. So it's 2 lots of that. 2 lots of that. So we've looked at this system from the point of view of P, the point of view of Q, and from the point of view of just the pulley. Now the M made that a little bit fiddly, so let's do, and this is from page 177, I believe, question 1. This is one where we've just got numbers. So can I get you to work out not just the tension, but the acceleration in this situation? Very, very similar to this. So consider just A and just B. Yes. Yes, sorry, let me just pause that. Sorry, I've just realised I didn't double this. So so it's 2A plus 2G. So sorry, it's 2 lots of 1.96 and 2 lots of 9.8. 23.52. N. 23.52 N. Thank you. And that means the force on the pulley is 47.04 M newtons. I was trying to do too much in my head there. Sorry about that. Thank you to Harrison for pointing that out. So for question 1 in exercise 10F, very similar, a bit nicer because you haven't got any missing values in there. So you've got 4 kilograms and 3 kilograms, so the 4 kilograms is going to go down. So here's my F equals ma statement for that left-hand side, F equals ma for that right-hand side, rewrite both as t equals, combine the 2 to give me my value of acceleration, and then I chose to use this, so I rewrote that, now I know A is 1.4, and that gave me the tension in one of the strings. Okay, so we know that this thing is accelerating, and we know it's a constant acceleration, so we are at liberty to use SUVAT. So what are we expected to do at this point? So when A has travelled a distance of 2 meters, it strikes the ground. and we want to know the speed of A when it hits the ground. So this is SUVAT, just like we did at the beginning. This is a SUVAT problem. We know that it started at rest. So we know that U is going to be 0, which makes it a little bit easier. We know the acceleration. And we want to know its V when it hits the ground, and that's after it's travelled 2 meters. Can you make sure you store your value of V? So are we happy that we can use SUVAT to work out the speed after 2 meters? Just so happens that after 2 meters it hits the ground. Now B doesn't hit the pulley, so what we've got here is here's the ground. It's A is at the ground. So we'll assume it's a really, really long string, and there's a pulley up here somewhere, but we're nowhere near hitting that pulley. So let's consider now B. We want to know the height that B reaches above its initial position. Okay? And for this we've got to do 2 separate journeys. So for the first 2 meters of its journey, it is connected to A. It is connected to A. So for the first 2 meters, it's just moving at 1.4 meters per second squared. So this is where it started, and we know that it has travelled 2 meters when A hits the ground. Okay, so we've got before A hits the ground, it travels 2 meters. We want to know how far it travels in total from where it starts. But B is not going to stop moving. It's going to keep on going up. Okay, the fact that A has hit the ground is not going to stop B moving. B is now going to keep going up. But it's no longer accelerating at 1.4 meters per second squared, because the string is now going to be slack, isn't it? There's no tension in that string anymore. So B is going to be going up, but its acceleration will be gravity. So if we now consider B after A hits the ground, is that what you were saying?
Yeah, I should agree.
Sorry. If we now consider B after A hits the ground, we want to know how far it travels before it reaches its maximum height. So I know it's now, and I'm going to consider up as positive, it's now being decelerated. The string is no longer relevant. It's now just moving under gravity. It's going to eventually, well, quite quickly, stop. And that's the maximum height. And at that point, its velocity will be 0. But what was its velocity at the start of this little sub-story? We've got that value there, haven't we? We've got that value there, which is a good job we stored it. It was 2.36. And we want to know how far it actually travels. So after A hits the ground, B is going to keep on moving, but it's no longer being tugged. It's now just, so that now is not relevant, it's now just moving under gravity. Gravity is slowing it down, and I want to know how far it goes before it stops moving. Obviously then it's going to start falling again, but mercifully we're not being asked that, we're just being asked how high it reaches. Don't forget, that's not the final answer, because we need to hit add 2 to it, because this part of the story only starts once it's travelled 2 minutes. See if we can finish up with that thing. So because I've done 9.8 is negative, I've got that. So I'm going to do my stored value squared, which of course I just square rooted it, hadn't I? So let's save that. And I'm going to divide that by 2 times 9.8. Which gives me 0.285. So S is 0.2857, so that's 286. Add that to 2 gives you, so the total distance is 2.286 metres. Which of course we should round to 2.29 if we're going to 3 sigma figures, because I've added that one. Yes, so pulleys are quite fiddly, and we've got quite a bit more of pulley work to do. So more of that tomorrow.